right? But this is Riemann sums now using the definite integral. So it's not in the notebook. I apologize. I think I hate it so much I purposely didn't put it in the book. But here it is. I decided I really can't skip it. So I'm going to put a little bit of writing up here. Let's go ahead and make just an axis here. And we're going to label this from 1 to 2. And again, I'm going to try to describe where all this is coming from. That is my goal for you to understand. All right, and I have just some sort of increasing function here. All right, so hopefully you can picture Riemann sums. That's what we've been talking about. You can picture if you built, don't draw it in, but if you build a left, you would go up on the left till you hit, come over, make a rectangle, or a trapezoid, whatever shape we're talking about. We're going to focus on just rectangles here. Okay, so I'm going to start with 2 and just kind of jot it down. We'll try to talk this out. 2 subintervals. Okay, and I'm going to use these 2 words. I'm going to call it static and dynamic. Okay, so static is something that doesn't change. Dynamic is something that's constantly changing, right? So if I was to build a right-handed rectangle with 2 subintervals from 1 to 2, how big would my base be? If I had to put 2 rectangles in here, each base would be 1/2. And that is static, right? That's not going to change. If I'm going to fit 2 rectangles in here, I'm going to say the base is automatically going to be 1/2. Okay, now for those of you that couldn't calculate 1/2 in your head, basically this has a difference of 1, and you're dividing it into 2, right? So in theory, I'm saying it's 2 minus 1 divided by 2. I'm taking that distance and dividing it by 2. And I'm going to say that's a static amount. That is always going to be 1/2 if I'm putting 2 subintervals. So I'm just going to draw in 1/2 here. Draw on the first one. I'm going to go on the right, sorry, right-hand Riemann sum, and up on the right. So I'm going up on the right and over, up on the right and over. Okay. Now the dynamic part, the part that's going to change, is the height. The height is not the same. This is an increasing function. So the height is not going to stay the same. Okay, so the first height on the right, so if this is my left and this is my right, my first height on the right would be the right at 1/2. I would first have to find the height at 3/2. And then I'd also have to find the height on the right at, for this rectangle, the height on the right is 2. So that's constantly changing, right? It's dynamic. Depending on how many intervals, that's going to change. So I'm going to say my approximate integral would be, I'm just going to call it area for the time being. My first rectangle would be a base of 1/2. And the height on the right would be 3/2, so times f of 3/2, 1/2. Plus a base of 1/2 for the second rectangle, and now I would need the height at 2. Bless you. Does that make sense to you? Base is 1/2, I want the height at 3/2. Base is 1/2, I want the height at 2. All right, so let's make it a little more interesting. What if we said instead of 2 subintervals, we want 4 subintervals? So I'm going to change this 2 into a 4. So the static part, the part that's not going to change again, would be the base. How big would the base be this time if I had to squeeze 4 subintervals in there? 1/4. 2 minus 1 is 1, right? I have a total of 1, and I'm dividing it by 4. So that would get me a base of 1/4. Now again, the height is the dynamic part. The height is always going to change based off where we have these bases. So I'm going to draw this one in as well. So I'm just going to cut these in half. So I'm going to put this one in, my right over. So there's my quarter. So again, I have to fit 4 of them in here. I'm going up on the right, and they each have a base of a quarter. Probably could have done that in a different color, but you get the idea. So again, I took a distance of 1, 2 minus 1 is 1, and divided it into 4. So now I'm going to have 4 areas. My first base, my static part, is going to be 1/4. That's not going to change. Times my height. So my height is going to be at 1 1/4, which is 5/4. Right, 1 1/4. Plus I'll have a base of 1/4. This time I'll go 6/4. I'm going out a quarter each time, right? Plus 1/4 times 7/4 plus 1/4 times 8/4, which obviously is 2. Okay, so if we broke them into quarters, I'm going 1 1/4, 1 2/4, 1 3/4, 1 4/4. Okay. Now I'm going to stop drawing here and just kind of write a couple of these out. If this time I went to 8 subintervals, okay, so again, I'm not going to draw all 8 in, but let's talk about what it would be. What would the base now be? 1/8. 1 to 2 is 1. I have 1 distance, and I'm dividing it by 8. So my static part, the part that's never going to change, is that the base is going to be 1/8. Okay, so now each of those heights on the right are going to change, right? So if I'm starting at 1, my area is going to be my base of 1/8 times f of 1 1/8, so f of 9/8. Plus, I'm going to keep going, my base is 1/8, and then I'd have 10/8 plus 11/8 plus, obviously it's going to keep going until I get to 2, which would be 16/8. Okay. Now, remember, we said, in theory, we want to put how many rectangles in there to get the exact area? An infinite amount, right? So I'm just trying to break this smaller and smaller and smaller. I'm going to do one more just to really stress this point, that we're really trying to put an infinite amount of rectangles in. So I'm going to go to 16 subintervals. So what would my base now be if I went to 16 subintervals? 1/16. So again, 2 minus 1 is 1 divided by 16. So the static part, the part that's not going to change, is they're going to be 1/16 bases. Okay, so my area is going to be 1/16 times the height at, that's why I'm saying f of, 1 1/16 or 17/16 plus 1/16 times f of 18/16. I'm going to say dot, dot, dot. If I want to end at 2, that's 1/16 plus f of 32/16. Okay. So what we want to catch here, all right, is that, again, the base is static. The base isn't going to change. Okay, we can easily figure out the base. But these numbers are really important. Okay? In each of these cases, this was 1 plus the base. Right? 7/16 is 16/16 1 plus the base of 1/16. In this case, this is 1 plus the base times 2. The next one's going to be 1 plus the base times 3, 1 plus the base times 4, 1 plus the base times 5. It's going to go up in that same fashion every single time. So here is the technical definition. And I'm just going to grab my highlighter. It says, let y be the function that's continuous on the interval. So we know it's continuous. We're going to take a to b and divide it into n equal subintervals. All right, so we're going to divide a to b into n equal subintervals, and kind of what we just did mentally, we're going to say that width is b minus a over n. Okay, now I think that's pretty easy to do. I'm going to go back here. The b minus a was 2 to my 1, so that was 1. If I had 2 subintervals, we took 2 minus 1 and divided it by 2. If we had 4 subintervals, we said 2 minus 1 divided by 4. 8 subintervals, 2 minus 1 divided by 8. So that's pretty simple for the base, and again, that's the static part. Okay. And again, n represents the number of rectangles. The right endpoints are noted by this. The length is f of a plus b minus a over n times k. Okay, so I'm going to come back and try to say that's what I tried to explain. This a value is 1, right? So we started at 1, plus the base, the b minus a over n, times 1. Then we said it's 1 plus the base times 2. 1 plus the base times 3, 1 plus the base times 4, all the way up to n. So remember, a Riemann sum is not the exact area. However, it can be proved that this right here is the exact area. Okay? So this is connecting a Riemann sum to the definite integral. So we're going to tackle a question you might see on the exam on how we're going to find this. So it says, find a limit expression. Okay, so we're going to use something like this to that's equal to this integral. Okay, so the first thing I want to do is I want to identify the width and the length. Okay, so the width is always b minus a over n. Okay, so this integral is going from 0 to 4. So that's going to be 4 minus 0 divided by n, the number of rectangles. I don't know how many, we're just going to call them n. Okay, so I have this function 2x squared plus 3, I don't know, looks something like this, from 0 to 4. Okay, and I want to squeeze in from 0 to 4 n rectangles. All right, and in theory, we want an infinite amount. So there's my width, pretty simple to get. The length. Okay, the length, we highlight it up here. It's f of a plus your b minus a over n times k. So f of, okay, so I'm just going to make a note again. A is where I start. This is my a value. This is my b value. So in this case, it's going to be 0 plus my b minus a over n, which is my 4 over n, times k. I'm just going to reduce my width to 4 over n instead of keeping the 0 there. Bless you. Okay, and then I'm going to clean this up because 0 plus anything is just itself, so I'm going to call this f of 4 over n times k. Once you have those two things, you're ready to write the expression. So you really just need your width and your length. Okay, now you're always going to put a times k. Sometimes they'll use an I. It doesn't matter what letter you pick. I'm just going to stick with k, but times something, because that's the part that's changing. When we did 1 plus the base times 1, 1 plus the base times 2, 1 plus the base times 3, etc. Okay, so now we're ready to write this limit expression. So I'm just going to go back to my integral here and say this is equal to the limit as n approaches infinity, because in theory I want an infinite amount of rectangles. N is the number of rectangles. I want infinite of them. I want to add from k equals 1 to n. So that part's never going to change. That will always be the exact same thing. Okay, so now I want f of, right, I want to plug this into my function. I want f of this value. So I'm going to go to my equation, and I'm going to say it's 2 times 4 over nk squared plus 3. I'm just finding f of 4 over nk. I'm replacing all my x's with 4 over nk. I'm going to put a bracket around that. And then you multiply by the b minus a over n. So I'm going to say times 4 over n. And then you cross your fingers and you hope that's a multiple choice. How's that? Now, if that wasn't the answer, really the only other thing they're going to do is do the math out on this. So I'm going to do it once. I'm probably not going to do it for everyone. I'm really going to hope that the answer is there. So what they could do, so I'm going to keep my limit here. The limit as n approaches infinity. The summation k equals 1 to n. PEMDAS, right? I can square this thing. So if I square this, would you agree that's 16 over n squared k squared? If I just square this term, bottom side. And then I have to multiply it by 2, it says. So I'm going to say this could be 32 over n squared k squared plus 3. Only if I didn't see my choice, times 4 over n. So this is new in the past 2 years. This has actually never been on the exam before until the past 2 years. They added this little piece in. Again, connecting the integral to the summation expression. So the two things you want to keep saying to yourself is you need a width and a length. And then we're going to put it all together. We're going to get this. All right, flip it to the next side. Let's start with our width. All right, so the width, you're saying to yourself, I'm going from 2 to 5, and I need to divide it by n rectangles. So I'll write out the formula, but I think you can do that in your head. B minus a over n. My b is 5, My 2 is the a over n. So I'm going to say my width is 3 over n. Does that feel okay? B minus a over n. I'm going from 2 to 5, and I'm dividing that into n rectangles at the distance of 3 over n. Okay, so now I need the height. This is the part that's going to change each time, right? Because we have to multiply it by 1, multiply it by 2, multiply it by 3. So the height is f of, I'm just going to keep saying it to myself, a plus my b minus a over n times k. It's a plus my width times k, basically. So I'm going to say it's f of, what's our a value here? 2, plus my b minus a over n is just 3 over n times k. And again, once you have those two things, we just got to get it into the formula. Okay? So now it's equivalent to the limit as n approaches infinity, because we want an infinite amount of rectangles. Okay? From k equals 1 to n. And now I have to find f of that. So I'm literally doing, if you're stuck on this part, you're literally saying it's the base times the height, or height times the base. So I'm going to start with the height. I need f of this. So every place I see an x, I'm substituting this in. So it's 8 times 2 plus 3 over n times k minus 2 plus 3 over n times k. Oops, I missed my k. Squared. Right, I'm just substituting it in for x. Okay, so that's my height. Now I have to multiply it by the base, and the base is my width, which is just times 3 over n. Okay, so again, it's just my height and my base. And that's it. You're not finding the value. You're just writing it as from the definite integral to the summation. Okay, now again, if I were to plug all these values in, I would get the exact area, since it's not actually a Riemann sum. It's a limit expression. All right, now we're going to go backwards. Now we have to be given the expression. We have to write the integral. Okay, so the first thing I kind of say to myself is, what's the base and what's the height? Well, the height is always the function, so that's the height. Therefore, this is the base. Okay. So I'm going to say to myself, my base formula is b minus a over n. And what are they telling me this is equivalent to? 3 over n. So I know b minus a has to equal 3, right? So if this was multiple choice, I would start looking at my integrals. If they're not different by 3, you can cross those off right away. Now, I should be able to figure out the a value. Okay, so I'm going to say, who did they sub into the function? What is their parentheses around? Who did they substitute in? If I had to say find f of something, who do you think they plugged in? Who's inside some parentheses? 5 plus 3n over k. This is my height. Okay, so if I go back to the rule, I have it written down in the previous one. It's f of a plus b minus a over n times k. I see that right here. I see my b minus a over n right here times k, so that's telling me this must be the what value? The a value. So a must equal 5. Okay. Now if I bring that back here, I should be able to figure out what b is. What minus 5 equals 3? 8, so b must equal 8. So I know this is the integral from, starting from 5 to 8. And we just plugged 5 plus 3 over nk into this function, so this must be my x. So this is literally just the sign of x. Okay, that's who I substituted that into. And this is all we're looking for, is the integral that has that. So again, once I saw this, I would definitely say I want to make sure my integral bounds are 3 apart and start eliminating any choices based off that. Like you can start narrowing probably 50% of them down. All right, I only got one more here. You ready? All right, example 4. The first thing I want to look for is my width. Now, typically we've been putting it at the end. This time, just to mess with you, they put it in the front. That doesn't matter at all. This is still my base, and this is still my height. Okay. Base and height. So I know my b minus a over n, my base, is equal to 5 over n. Okay. So I know I'm looking for a distance of 5 in my integral. That's the first thing I'm going to take note of. I need to have a gap of 5. Okay, now who was substituted in? Who did they find? F of who? I got to look for that 5 over n someplace, right? 5k over n minus 1. Okay, so based off that, this is my b minus a over n. This must be my what value? A. So a is equal to -1. So if b minus -1 has to equal 5, what do I know about my b value? B must equal 4, right? Because that's a +1, subtract the 1. B must equal 4. So I'm going to say this is the integral from -1 to 4. There's my distance of 5. Okay. And again, who did I plug 5k over n minus 1 into? Well, I plugged it in here, so there must have been an x. I plugged it in here, so there must have been an x. So I would say that's 2x squared plus x plus 4 dx. That's all I got. I don't know where we're at. We're going to try a couple more together on the homework. Okay, so we have to go backwards and forwards here. So we're going to have to, given the integral, write the summation, and then given the summation, write the integral. Let me pass this out here. I did put one of each on there tomorrow. With my phobia. I'm going to put it in the book. All right, let's try. All right, so this is a goofy little sheet. So this is box 1. So once you find your answer, it should be the answer to one of these questions. Okay, and then wherever you find it, you'll put a 2 there, and then play the game and keep going. So we'll do the first one together. Take a moment and try to write the limit expression. Remember, you need your width and your height. So I'll give you a moment, and then we'll compare. Your width and your height. What are we getting for the width? Does 4 over n sound good? Okay, and again, like I feel like that's a 10-second question. You could probably do b minus a over n in your head real quickly. 4 minus 0 over 4. All right, so the height is, and that's the part you got to memorize, it's a plus the b minus a over n times k. What's our a value here? So 0 plus my 4 over n times k, which is really just 4 over n times k. Okay, so now I'm going from the integral to the limit. So it's the limit. I want an infinite amount of rectangles from k equals 1 to n. Okay, and now I have to find f of 4 over nk. So I'm going to substitute that in. So 4 over nk squared plus 1. So again, that represents my height, and now I need times the base, or the width, which is 4 over n. And that's it. Now I'm just going to look for that answer. 4 over nk squared plus 1 times 4 over n. Okay, I don't see it anywhere, so I'm going to go one more step and maybe say maybe it has to get cleaned up a little more just because I didn't see it. Do you agree you could square this term? So I could be looking for 16 over n squared k squared plus 1 times the 4 over n. So if I don't see my answer, then I'll take it a step further. I really just hope I see my answer. 16 over n squared k squared. I think I see that here on the next page. 16 over n squared k squared plus 1 times 4 over n. Okay, so that is my number 2. Then we'll tackle this one. You'll find that answer, and that will be 3. And it should take you through all 16 questions, okay? The answer should be in there someplace. So go ahead and start that second one, and we'll compare. So I got a base, I said pi over 2 minus 0 over n, or I just multiplied the top and bottom by 2, so I had pi over 2n. And then my height is f of a plus the change in the width times k. So I'm saying I'm going to find f of pi over 2n times k. And then put it all together in that limit notation. So I will obviously be around 9th period. If you have any questions with this, stop down during the Calc Lab or any other time during the day. But all the answers should match up to something. And then we're going to test tomorrow instead. I think you have that spiral as well, and a lot of people got it done last week.